Hello everyone and welcome back to the channel. In the world of distributed systems, data isn't just in one place. It is replicated across many servers. But how do all these separate machines agree on a single consistent truth, especially when network issues or server crashes occur? This is a fundamental challenge solved by consensus algorithms. In system design reviews, discussing these algorithms show you understand the very core of building high, consistent, and fault-tolerant distributed systems. Today, we are diving into what they are, why they are crucial, and the key algorithms you should know. Okay, so let's start. First, let's try to understand the problem. The problem at the heartbeat of consensus algorithms is quite simple. How do a group of distributed nodes agree on a single value or a sequence of decisions, even if some of them fail or can't communicate reliably? You need to imagine like a distributed database, okay? Let's assume that we have like a distributed database, we have different nodes. We have N1, N2, and N3. We have these servers. Or let's call it like NA or server A, server B, and server C, or whatever it will be. So let's imagine that we have, if node number A updates a record, how node B and C know about that record? How does this happen? And more importantly, how they agree on exact order of the update relative to other updates, even if node A crashes midway or the network briefly splits. This is the distributed consensus problem. Without a robust solution, replicas can diverge, leading to data inconsistency, incorrect status, and system chaos. This sets the stage for algorithms like Paxos and Raft. Okay? So, what are consensus algorithms? They are a protocol that allow group of distributed processes to reach an agreement on a single data value or a sequence of decision, even if the presence of various failures. Okay? Even in the presence of various failures, such as server crashes, network delays, or packet loss. The goal here to guarantee two critical properties. Number one, safety. Basically, the system never commits an incorrect or conflicting value. All non-failing nodes agree on the same value. Number two, liveness. Basically, all non-failing nodes eventually do agree on a value, ensuring the progress. So if we want to talk about the analogy, you need to think of a group of democratic leaders trying to agree on a simple new law. Even if some members are absent or have communication issues, the protocol ensures that ultimately everyone passes the same law and the system continues to make the progress. Okay, so let's talk about some key guarantees of consistent algorithms. First, we have agreement, which is consistency. All non-failing nodes decide on the same value. Number two, validity. Only a value that was actually proposed by a node can be chosen. Okay? Like there is no arbitrary values. Number three, termination or liveness. All non-failing nodes eventually will reach a specific decision. Number four, fault tolerance. Agreement is achieved even if a major of nodes, for example, if you have 5 nodes consensus and if you have 5 nodes, consensus can often tolerate 2 failures, for example, requiring a majority of 3. Okay? So, next let's talk about the common algorithms. First we have Paxos. Paxos is often considered the theoretical benchmark for consensus algorithms. It involves a complex dance between proposers who suggest values and acceptors who vote on values and learners who learn the chosen value. It typically uses a multi-phase comment-like process. The pros of this one, it's highly fault tolerant, mathematically proven correct, foundationally for many distributed systems. The cons of it is famously difficult to understand, implement, and debug correctly. It's often said that no one implement Paxos. They implement something like Paxos, but it's simpler because it's really hard. Next we have, it's used in Google Choppy, Look service, and also it's used in Apache Zookeeper. Next we talk about Raft. Raft is designed specifically for understandability. Raft simplifies consensus into more manageable set of rules, focus on leader election, log replication, and safety mechanisms. The system first elects a single leader, and all changes go through this leader, who then replicates them to the followers. The pros of this one, it's much simpler to understand and implement correctly than Paxos. Has a strong safety guarantees and is becoming very widely adopted. The cons of it still involves significant distributed system complexity. It's used in key value stores. It's used in what else? I guess key value stores and some databases, some like SQL databases. Cockroach database also as well, I guess, using it. And yeah, this is what comes to my mind. Okay, so why consensus algorithm matters? It matters because of different things. We will mention 5 of them on this video. The first, we have distributed data consistency, like ensuring that all replicas in a distributed database or key value store maintain the same consistent state. Number 2, leader election. Reliable electing a single primary or leader in a single or in a cluster for tasks like coordination or handling rights. Number 3, distributed locks, guaranteeing that only one process holds a critical lock across many machines. Number 4, configuration management, ensuring all nodes in a cluster agree on the same shared configuration values. Number 5, interview focus. It's about interview focus, which I would say bringing up consensus show a deep appreciation for the complexities of building truly reliable and consistent distributed systems, moving beyond pacing replication to strong agreement. So I would say I want also to continue on that, like in an interview, when you discuss critical shared state, leader election, or strong consistency guarantees in distributed system, this is your cue to mention consistent algorithms. You don't need to implement them from scratch, I guess, but explain their purpose and the trade-offs. Mention Raft as more understandable and practical algorithm for real-world scenarios. You need to connect it to the CAP theorem, which is nothing that these algorithms typically prioritize consistency and partition tolerance. Yeah. So yeah. Noting. Sorry, noting. You need to note that these algorithms typically prioritize consistency and partition tolerance. Sorry for my mispronunciation. Mispronunciation. Yeah. So yeah, that's it for this video, and see you in the future.